Yes, we're recording. I got audio. Excellent. I do have audio. Show me some audio. Yep, there's audio. Okay. The question you have to ask is, why is the variance, or by extension the standard deviation, of a sample always less than the variance or standard deviation of the population? Why isn't it just as likely to be a little bit more as it is to be a little bit less? That's the real question. And it's always going to be a little bit less because in order to stop the variance from always balancing out to zero, you take the square of the variance, which forces it to be positive. Okay. Now, what's the other one? This one makes the point even easier. What is the range of the data? X max minus X min. That's true whether we're talking about the range of a population or a sample. Okay? What's the range of a sample compared to the range of a population? It's the maximum and minimum of the data values that you select. Unless you just happen to select this and this, unless you just happen to select both of those two data in your sample, then it's guaranteed that the range of your sample is going to be less than the range of your population. Because it is so highly improbable that it is statistically the functional equivalent of impossible that you're just going to happen to grab, when you randomly sample this data from this population, that you're just going to, by a random chance, happen to pick the very highest and the very lowest data points. It's so improbable as to be tantamount to impossible. But it is in fact mathematically impossible that the range of your sample could ever be greater than the range of the population. In fact, what you're going to find is that it will always be less. Same thing is true of the standard deviation and more specifically of the variance, because you don't take the variance, you take the square of the variance as the population variance, which makes it always positive, which means it's always going to be greater than the variance of the sample. That's why when we divide the sample, instead of dividing by n, we divide by n minus 1 to force that sample variance or standard deviation to be just a little bit bigger, a little bit larger than it was. And that way we will, you will more closely approximate the same value, the parameter. And remember, we're talking about statistic versus a parameter. Right. So by dividing the statistic by n minus 1, we force it to be a better approximation of the parameter that it's associated. Okay. That's the objective. That's the idea there. And you'd be amazed at how many people don't realize that. They don't know that. They don't think about it because they don't care. It's like, well, I learn the formula and I plug in the values and I just notice I do n minus 1, and I don't know why. There's a reason for it, and that's the reason. Because you're never going to get a sample variance greater than the population variance. And I would also point out that if you have less than 30 data, then n minus 1 is going to be a more significant increase than if n is greater than 30. Okay? If n is 100, dividing by 99 versus dividing by 100, it's not going to be that much of a difference. If n is 20, dividing by 19 instead of 20 is going to make more of a difference. So, and at the end of the day, it's all about probabilities and confidences, certainty, as opposed to, see, that's why I don't like calling it certainty, because to me, certainty is an absolute. If you are certain of the value, then then the probability is 1. But we don't get probabilities of 1. We get probabilities of 99 or 97 or something. Well, so far we've discussed measures, and they are measures. They are quantifiable numbers that we can calculate of central position.
Yes.
And we've looked at measures of variance. And in fact, we looked at the standard deviation, the variance and the standard deviation. And if that is our distribution curve, that's our mean. And in this case, because our standard deviations that's approximately 1 standard deviation. What if that standard deviation were larger? That's if the standard deviation is this much. What if the standard deviation were this much? What would that tell you about the distribution?
The distribution is more spread out.
It's more spread out. It's fatter. So this one would look something like this. It would be broader and shorter. Whereas if you had a standard deviation of this, then your distribution would look more like this. Okay? The picture that I've drawn there is to give you Thomas, ¿qué pasa? The picture I've drawn there is to give you a qualitative understanding of what that measure, variance, or standard deviation, what it actually means. You look at a population and its distribution, you can tell something about the shape by looking at the measures of central, what are the words, central or something? Central tendency, thank you. You got the mean, the mode, the mid-range, the range, you've got all of these things that give you idea about the shape of your distribution. How close are they to each other? You know, if they're does it make the thing more right skewed or left skewed? Is it normal? Is it a normal distribution? Well, this variance in the standard deviation tells you something about how tight and how packed or how spread out it is. How narrow as it gets narrower, it gets taller. As it gets more spread out, it gets flatter. Because why is that the case? Why does it have to get taller because it got narrower?
Compressing the range.
No, in fact, the narrower it gets, the more you compress the range. Why do you think?
It's like it's just taking it, kind of mushing it.
And that's exactly what's happening. As you're mushing, it's like squeezing the air in a balloon. You can squeeze it in from here, it's going to get bigger here. Squeeze it down, it's going to spread out there. Mortgage brokers love to play that game. They'll take all those they'll take those points and they'll squeeze them in, squeeze down your rate, but you'll end up with a bigger and bigger, upfront cost, or they'll give you a lower upfront cost by pushing all that money out into higher points that you pay on the long range. But none of it ever goes away. The reason this happens here, the reason you won't see this distribution and that distribution is because this is called the normalized or the normal distribution. That means the area under the curve, if you take and integrate this thing from negative infinity to plus infinity, it will equal 1. Okay, it will always equal 1. So, that means that your peak is always going to be less than 1. The normalized. But it also means that that's why when you have it spread out, the amplitude comes down, or the height. And as you squeeze it tighter into a closer, more dense distribution, that peak gets taller and taller. So, that is our measure of central tendency and our measure of variance. What is the shape of this? How fat and tall is it? How skinny and tall? How fat and short? But that only describes the distribution as a whole. What if we want to start talking about particular data in the distribution? Do you have any homework? If we want to talk about a particular datum, then we also need measures of position. And that's what we're going to talk about today in 3.3 or 3-3. The first one we're going to talk about is the z-score. Now, you've heard it said that you can't compare apples and oranges. And that's basically true. In my physics class, I harp on making sure your units match. You can't add seconds to meters. You can multiply meters by seconds, but you can't add them. You're going to add two numbers, they have to have the same units. So, what's the example they use here? Say a student scored 90 on a music test and 45 on an English exam. What does that tell you?
They're better at music than they are English.
That might seem reasonable, but that's not right. Because we don't know how those scores compare. In order to make a meaningful comparison, we need to make them, well, common. We need to make them now, this much is always true. Whoever scores the median value, whoever score is equal to the median value, they did better than, they're right at the 50% mark. They did better than half the students in the group. The question then is, what's the median for that particular class? So he may have scored 90 on his music exam, but that may have been 90 out of a possible 200. Whereas he scored 45 on his English exam out of a possible 50. So, there's always that. The z-score is also called the standard score. It's the value that you get when you subtract the mean of the distribution from that particular datum. And then you divide that result, the difference, by the standard deviation of the distribution. Let's see. Or now, that's easy enough to calculate, but it's probably not very meaningful yet. So, let's back up and look at this one little step at a time. What is this value here? The datum minus the mean. What is that? That's how far this score is from the 50% mark, from the median, from the average, from the mean. Okay? When you divide it by the standard deviation, you're basically changing it to how many standard deviations this score is from the mean. Okay? What if someone scored exactly sigma out of the whole population? Let's say the population is we're talking about the whole population instead of sample. Someone scores exactly one standard deviation above the mean. Well, if the mean is 25 and the standard deviation is 6, 6 minus 25, well, actually, if they scored 6, that wouldn't be their data. That would be, if they scored exactly one standard deviation above the mean, and the mean is 25 and the standard deviation is 6, then they scored 31. Okay? Well, when you take 31 and you subtract from it 25, you're left with 6, and you divide that by the standard deviation of 6. Their standard score then is 1. They scored exactly 1 standard deviation above the mean. You see what I'm saying? You see how this works? If they scored 19 and you subtract 25 from 19, you get minus 6. And you divide that by 6. At 19, they scored exactly 1 standard deviation below the mean, or got a minus 1 for their z-score. What if they scored exactly the mean? So the mean in this sampling, in this population was, these scores, the mean value is 25. What is their z-score, their standard score, if they score exactly the mean? Their standard score is 0. So, this is how the standard score works. You take the distribution and you define the mean as 0. And you know the standard deviation. Now, you look at someone's score, their score might be 95 or 45. That doesn't tell you anything. But if their standard score is 2, then you know they scored 2 standard deviations above the mean. If it's 2.5, they scored even higher. If it's minus 1, then you know they're over here in the distribution. The point is, this standard score, the z-score, gives you a quantifiable measure of where that score is in the distribution. And it actually makes it kind of easy for you to visualize as well. Remember, this is called, we're studying, what we're looking at right now, these measures, measure of central tendency, measure of variance, measure of position. These are what are called descriptive statistics or descriptive parameters if we're talking about the whole population. And that's what that means. It means you get this number, you get this z-score for that particular datum, and that gives you a visual of where they are in the distribution. Like with the Chebyshev rule, it applied, this is always going to apply regardless of the distribution. It's going to be most meaningful when you have a normalized distribution. I guess I shouldn't say that. It's going to be easier for you to just visualize if it's a normal distribution. If it's not a normal distribution, if it's bimodal, if it's U-shaped or skewed or multimodal or whatever else, these parameters are still going to be valid but you might have to, just like with the Chebyshev rule, you're still going to be able to apply that. You're going to be able to make that estimate on how many, where something is in the distribution, of what percentage of the distribution is within that many standard deviations. But when it's a normal distribution, when the mean, the mode, the median, the mid-range all come to the same value, now you've got a normal distribution. Suddenly these standard deviations become even more meaningful. Remember the Chebyshev rule. The percentage of a distribution that is within k standard deviations of the mean is what? 1 minus 1 over k?
K, 1 minus 1 over k squared.
1 minus 1 over k squared. So, we did the calculation. That meant that if you were minus 3 standard deviation, if you were at plus or minus 3 standard deviations, you had, what, like 95% or 90%, something like that? Yeah. But that's for any distribution. So what the Chebyshev rule actually says is that you will have at least this percentage, maybe more, but at least this percentage within that, within that range of that number of standard deviation. But we also talked about the measures of central tendency, the mode, the median, the mean, and how they describe the shape of the distribution, and that if they were all equal, if the mean was equal to the median, was equal to the, if it was unimodal, it had the mean and the median and the mid-range were all the same, then that's when you call it a normal distribution. And at that point, plus or minus 3 standard deviations isn't just 90% of the population, it's 99.7% of the population. So, a z-score on a normal distribution is going to give you even more information about where, or more accurate information about where in the population, or in the distribution, what the population that datum is going to fall. Now, we've also got percentiles. And again, I'm going to go back and work with the normal distribution. This is easier. That's about 3 standard deviations. That means from here to here is 99.7% all of the data in that population. So that means everything from plus 3 standard deviations and on, or minus 3 standard deviations and less, together are going to equal only 0.3% of the population. That means from here down on this side, 0.15% of the population. And from here on up is 0.15% of the population. Now, if you divide the distribution into 100 equal parts, then you can talk about position by talking about which percentile a datum falls in. And if you've ever taken an SAT or an ACT or any standardized test, that's why they call it standardized, because the Z-score is the standard score. It's the standardized way of analyzing the position of a particular datum in a distribution. So, y'all took ACTs or SATs or both?
I did ACTs.
And you got your grade report. It told you you're in the 94th percentile, or the 98th percentile, or the 35th percentile. Okay? Point is, you score the mean, you're in the 50th percentile. Did y'all read the book for class?
I got to percentiles.
Okay, well, the way you do it, the way you calculate it, is basically you're doing an ogive. They point out in the book that most of the time you're going to find these things, these tables already generated and graphed out for you, and then it's just a matter, like they show on this page, on page 159, they show this one here. That is weights of girls by age and percentiles. So if you want to know where an 82-pound girl who's 11 years old, where she falls within her, within the distribution of 11-year-old girls by weight, you find 82 pounds on the vertical axis and find her age of 11 years on the horizontal axis, move across and up until the two meet, and you see they meet on the 50th percentile. Right on the 50th percentile, which means she's exactly average for her age. You both looking at the graph? Let's do this as an exercise. Thomas. Where would a girl who was 12 years old be if she weighed 120 pounds? Say again? No. Go up the 12-year-old line vertically until you get to the 100. What did I say? 110 or 120? 120. So you follow 12 up to 120, and you'll notice that that's just bit below the 90th percentile, which means you would have to interpolate. How many of these grid marks are there between the 75th and the 90th? One. It's like 1.5. 2, 3, 4, 5, 6, 7 and a half, so that would be 8. Each one of those grid marks represents 1/8 of this 90 minus 75 is 15, so 15 divided by 8 is roughly 0.5% for each, or would that be 2%? Now the point is, you look and you see that she's right just about 2% below the 90th percentile, so she's about 88 or 89%, somewhere around in there. Around the 88th, 89th percentile. You see how that worked?
This is the one on page 159.
Right. Each one of the blue curves represents the percentile of if you took, here's a way to envision this graph. Take data for girls on how much they weigh, starting with age 2. Well, there you see where all of those lines, those blue lines meet. That represents this distribution. Okay, and that all of that distribution is right there in the vertical axis, where those how many lines that is meet. Okay. It's like saying, here's this percentile, this one, 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 this one. Now you move over and you take the same data for all of the 3-year-old girls. Well, they're a year older, they've grown a lot. Now their distribution is bigger, more spread out. Actually, it would be more like Then you do the same thing for all of the 4-year-old girls. You get that? I should have started with a much taller graph. But you get the idea. In fact, let me redo that just to make the point. There's all your 2-year-old girls. There's all your 3-year-old girls. There's all your 4-year-old girls. 5-year-olds. 6-year-olds. Etc. Then you get the percentiles for each of you divide each of these distributions into hundreds, into 100 equal parts, and you come up with their percentiles. And in the case of the 2-year-olds, you find out that they are all between 22 and 32 pounds. All of them. By the time they get to 11, only about 5% of them are going to be less than 60 pounds, and only about 5% of them are going to be more than 125 pounds. So you've got 90% of all of the girls at 11 years old are going to be between 60 and 125 pounds. You see how that works? Here at 11, 5 percentile is at 60. And the 95th percentile is here at 125. So that 90% of the girls are going to be between 60 and 125 pounds. And then you can find out that for an 11-year-old, weighs 82 pounds, she's right at the median, right at the 50th percentile for her age group. See if you can read this graph. What percentile would a 14-year-old girl be in if she weighed 100 pounds?
Should be in the 25th percentile.
She would be in the 25th percentile, which means, where would she be in this graph?
Should be.
That's the median, that's the 50th percentile.
Should be.
It should be somewhere in this area here. The low side of the distribution. Thomas, I'll give you another one to see what you can tell me. 15-year-old girl weighs 155 pounds. Where would she be in this distribution? This one. So go to the chart. What percentile is she in? Year-old girl weighs 155 pounds. Let's see. 15-year-old girl, right here. She weighs 155 pounds. This is the 90th percentile. This is the 75th percentile. If she's here, that means she's in the 95th. She's in the 90th percentile. Now, if she was like at 150, then she'd be a little below the 90th percentile, like the 85th or the 88th or something. But 90th percentile, I mean, she's way over here. That's a big girl for her age. Let's look through the example of systolic blood pressure data and see how they turn these into percentiles. We've got this tabulated frequency group data with class boundaries. And I'm going to need y'all to read the data to me so I can write it down and I have this. Keep going back to the book. We've got class boundaries of 89.5 to 104.5.
It's 104.5 to 119.5.
Next,
119.5 to 134.5.
next,
134.5 to 149.5. Then 149.5 to 164.5.
when somebody's about to die, what's next? Or is that the top?
164.5 to 179.5.
Is that it?
Yes.
Okay, so anyone coming up on 180 milligrams per deciliter, or whatever that is. I forget the units. It's pressure, some unit of pressure. diastolic of 180, you need to see a doctor. You may not be about to die, but you're getting close. All right, now let's look at the frequency data. You got 24, 62, 72, 26, 12, and 4. What's that total up to? 200. Okay. Now, just like we were going to construct an ogive, what's our cumulative frequency at less than or equal to 104.5? 24. Our cumulative frequency less than 119.5 is, did I do that right? 86. 24 plus 62.
Yes, sir.
Okay. Now, to get our cumulative frequency less than or equal to 134.5, we add 72 to 86. 8, 8 and 7 is what, 150? 158. All right, add 26 to that. 184 is our cumulative frequency less than or equal to 149.5. Add 12 to that.
196.
196. Add 4 to that, and we get 200. Boom. That's our total cumulative frequency less than or equal to 179.5. We could now plot an ogive based on those frequencies. But what we want to do is come up with our cumulative percentage. So, at less than or equal to 104.5, 24 is what percentage of 200? 24 divided by 200 is
0.12.
So that would be 12%. 86 divided by 200. 43%. 158.
0.79.
79%. 184.
0.92.
And 196.
0.98.
98%, and 200 would give us 1.00 or 100%. So now, if we want to talk about any one of these 24 data, we would say they were in the 12th percentile. If we wanted to talk about one of these 72, they would be in the 79th percentile. One of these 4 is in the 100th percentile. Or they're somewhere above. They are above the 98th percentile. So that might be how you talk about it. The first 24 are in the 12th percentile. These would be in the 100th percentile, or they would be above the 98th percentile. And that is how you do percentiles. You see how approximating a score, doing a z-score makes it a standard score, talks about its position in terms of how many standard deviations it is from the mean. More frequently, you're going to find data presented as being in percentiles. Now, there are others, and they talk about two of them in the book here: quartiles and deciles. So, since neither of you've read this far, without looking at the book, just give me a guess. What do you think the quartile means? What do you think that would mean to say that something is in a certain quartile? What's a quart? 1/4 quarter. So you divide the population into 4 equal parts, and you have 4 quartiles. So the first 25% would be the first quartile. From the 25th to the 50th percent would be the second quartile. From 50 to 75 would be the third quartile. Now, bearing that in mind, what's your best guess for what a decile is? And yeah, think of decimal. Just divide the population into 10 people instead of 100 groups. So the first decile is the first 10 percentiles. The second decile would be the 20th percentile. I'm not going to tell you that I don't do a lot of statistical data analysis, so I'm not going to tell you that you'll never run into those. You might. But all I really care about is that you understand what they are and know how to deal with them. There's a table 3-4 on page 165 that shows how they're abbreviated. The standard score is the z-score, abbreviated Z. Percentile is abbreviated P sub n. Decile is D sub n. Quartile is Q sub n. And they put a lot of creative thinking into that. One last thing I want to talk about before we call it a day. What's an outlier? What is it? What do you think an outlier is?
The one datum that doesn't fit with what's
Exactly what an outlier is. It's that one datum that is everything else is, look at your scatter plot. You got all of these data points and that. Okay, that's your outlier. Okay, and I will tell you, there is absolutely nothing wrong with tossing out an outlier if you can show that it is truly an outlier. Why would you think that might be the case? Why would it be okay to throw this data point out? To just disregard it?
say when comparing it to the rest, it's nothing.
The point is that you took a sample of a population. You already know that the population extends much further than your sample. Okay? Just because you happen to pick that one datum that was way outside the range of everything else doesn't necessarily mean anything. What we will find is that many of the measures that we talk about, the parameters and statistics, some of them are very sensitive to outliers. An outlier will change it dramatically. Others not so much. that's one of the things you have to think about. But at the end of the day, what you're trying to do is accurately describe and predict a population based on, or you're trying to describe a population based on statistics, not precision measurement. So you're dealing with probabilities. You're not trying to say, yes, the fourth ball chosen in this lotto is going to be 32. You can't do that. But you can talk about what you can. There are other things you can make predictions about with quantifiable levels of confidence. Look at the example 3-36. We've got the data set 5, 6, 12, 13, 15, 18, 22, and 50. Which of those do you think might be an outlier? Yeah. Because it's more than twice any of the rest of them. Every other data is within a factor of 2 of the data next to it, the datum next to it. Except that last one. So it would be very suspect. And they list here some steps for checking for an outlier. And so look at the quartiles. And after I just finished telling you you're probably never going to use quartiles, now they're telling you this is one of the times you will. Look at it, where does it fall at in the interquartile range?
Q3.
Yeah. Well, up here on the table above, forget about the example, look at the table above. It says arrange the data in order from lowest to highest. Find Q1 and Q3. What's the first quartile and the third quartile? Okay. Find the interquartile range, which is the middle half. Okay. Everything from Q1 to Q3 is the middle 2 quartiles, the middle half. Multiply that by 1.5 and subtract the value of 1.5 of the quartile, the interquartile range, 1.5 times the interquartile range from Q1. Add the value obtained in step 3. Add the interquartile range to Q3. If any of the data is outside of those limits, then you can consider that an outlier in this regard. Okay. Here's what we're saying. Here's your datums. You've got all of these datums making up this data set. Divide it into fourths. Here's Q1. Here's Q3. Here's your middle 2 quartiles. That's 8 of them. Multiply that by 1.5. That gives you take 1.5 of this, which would be 1, 2, 3, 4. So 1.5, that would be 6. You go 1, 2, 3, 4, 5, 6 here. And then you add those same amount to the other end of your range. And that gives you this wide window. It gives you this wide range. Now, any datum that falls outside of that range, you can disregard it as being an outlier. Any data in the set that is less than Q1 minus 1.5, the IQR, the interquartile range, is, is an outlier. Anything that's greater than 1.5 of the 1.5 times the interquartile range above Q3 is, again, considered an outlier. You don't want to throw out data because it doesn't fit. Okay, that's not good statistical analysis. Just the fact that the data doesn't fit what you expect, frankly, that probably tells you your expectations are wrong. Okay, but not always. There are times when outliers will just mess things up. And if it really is that far out from the rest of the data, then you can safely ignore it. And yes, I see we're out of time. So I will see y'all on Friday.